Most organizations believe they have the right maintenance strategy, but their results often say otherwise. One of the biggest mistakes in maintenance is trying to apply a single strategy to every piece of equipment. On paper, it may seem efficient, but in practice, it often leads to poor performance, unnecessary cost, and repeated failures. Because here's the reality. There is no one-size-fits-all maintenance strategy. What works in a bottling plant may not work in a power station, and what works in a small workshop may completely fail in an offshore environment. The right strategy depends on understanding your assets and the risk connected to them. So the real question is not which strategy is best, it is which strategy is right for this specific asset. And to answer that, professionals don't guess. They follow a structured decision process. One practical way to approach this is through 6 key criteria, what I call the C-FRaMPS framework. C-FRaMPS is a simple decision tool used to match the right maintenance strategy to the right asset. Each letter represents a critical question every maintenance team must answer before choosing how an asset should be maintained. Criteria 1. Asset criticality. How important is the asset? Before choosing any strategy, you must know how critical each asset is to your operations. Think of it this way. If an asset fails and nothing serious happens, it is low criticality. But if failure leads to downtime, revenue loss, safety issues, or environmental harm, then it is high criticality. Therefore, critical assets need strong preventive or predictive strategies, while non-critical assets may survive with basic preventive or even corrective maintenance. For example, in a power generation company like Siemens Energy, a gas turbine is classified as a highly critical asset. A single failure can shut down the entire plant, cause massive revenue loss, and disrupt power supply to thousands of customers. In contrast, a lighting fixture in the administrative office of the same facility is non-critical. If it fails, operations continue without impact. That difference in criticality is why turbines receive predictive monitoring, while light fixtures are often run to failure. Criteria 2. Failure modes. How does the asset fail? Failure mode simply means the specific way an asset can fail. You can't choose the right maintenance strategy unless you first understand how, why, and when an asset is likely to fail. Failure modes generally fall into 3 categories. A. Gradual failures, such as bearing wear or corrosion. These develop over time and are ideal for condition-based maintenance, CBM, or predictive maintenance, PDM. B. Sudden failures, like a blown fuse or an electronic board burnout. These occur without warning and are best managed with time-based preventive maintenance or, where acceptable, a run-to-failure approach. C. Hidden failures. For example, a fire alarm that doesn't trigger. These are not obvious during normal operation and require failure finding, detective maintenance, to ensure the protective function works when needed. For example, at companies like Shell, rotating equipment, such as pumps and compressors, often fail gradually through bearing wear, seal degradation, or lubrication breakdown. Because these failure modes develop over time, they rely heavily on vibration analysis and oil condition monitoring. On the other hand, electronic control modules in the same facilities can fail suddenly due to voltage spikes or component burnout, making them harder to predict and better suited for time-based replacement or redundancy. Understanding the failure mode determines whether the company invests in predictive tools or accepts corrective maintenance. Criteria 3. Risk and consequences. What is the worst that can happen? Every asset has consequences when it fails. They usually fall into 4 groups. Group A, safety, can someone get injured? Group B, environmental, can it lead to spills or pollution? Group C, operational, will it stop production? Group D, financial, what is the cost of repair or lost production? If the consequences are severe, the maintenance strategy must be proactive, data-driven, and reliable. If the consequences are mild, a simpler, cheaper strategy may be enough. For example, in a refinery operated by companies like ExxonMobil, the failure of a pressure relief valve carries severe safety and environmental consequences. A single malfunction can lead to fires, explosions, or toxic releases. Because the risk is high, these assets are maintained using strict inspection intervals, testing routines, and regulatory-driven maintenance programs. By contrast, the failure of a warehouse exhaust fan may cause discomfort but carries minimal risk, allowing for a simpler maintenance approach. Criteria 4. Maintenance cost. Is prevention cheaper than failure? Maintenance is an investment, But not all assets justify expensive techniques like vibration analysis or oil spectroscopy. Your decision should answer one simple question: is it cheaper to prevent the failure or to allow the failure and repair it? For low-value assets, run to failure may actually be the smartest choice. For high-value assets, preventive or predictive maintenance saves millions. For example, at companies like Toyota, critical robotic arms on an automotive assembly line are monitored continuously. Although predictive maintenance tools are expensive, an unexpected failure could halt production and cost millions per hour. Meanwhile, low-cost assets such as handheld tools or portable fans are often allowed to run to failure because the cost of prevention would exceed the cost of replacement. The decision is not emotional, it is purely economic. Criteria 5. Production impact. Will failure stop or slow operations? Some assets like bottling plant conveyor motor, power plant feedwater pump, and cement plant kiln fan are production critical. If they fail, everything stops. For these types of assets, downtime is expensive, so the maintenance strategy must focus on prevention and performance monitoring. Assets with minimal production impact can use simpler strategies without major consequences. For example, in a Coca-Cola bottling plant, a single conveyor motor failure can stop the entire production line, leading to missed delivery targets and lost revenue. Because of this production impact, such motors are placed on preventive schedules and closely monitored. In contrast, auxiliary equipment that does not directly affect throughput may be maintained using simpler strategies without major operational consequences. Criteria 6. Safety implications. Can failure put people at risk? In any organization, safety is the highest priority. If an asset has the potential to injure workers, cause a fire, lead to explosions, or create hazardous conditions, then a reactive approach is never acceptable. Such assets require preventive maintenance, predictive monitoring, failure-finding tests, and strict inspection schedules. When safety is involved, the right strategy is always the one that removes or reduces risk to the lowest possible level. For example, in offshore operations run by companies like Total Energies or BP, safety-critical systems such as fire and gas detection, emergency shutdown valves, and blowout preventers are never allowed to fail unnoticed. These systems undergo routine testing, inspections, and failure-finding maintenance, even if they appear to be working. When human lives are at risk, reactive maintenance is not a strategy, it is a liability. Now, putting it all together, choosing the right maintenance strategy is not guesswork. It is a structured decision-making process based on 1. How critical the asset is. 2. How the asset fails. 3. What the consequences are. 4. What the failure costs. 5. How it affects production. 6. And whether safety is involved. The goal is simple. Use the most cost-effective strategy that keeps your equipment reliable, your operation stable, and your people safe. And that's it for this video. Thank you for watching. If you found value in this content, please give it a like and share it with your team. Subscribe for more practical engineering and maintenance insights, and make sure you watch our next video. How top companies design their maintenance systems. Until next time, stay reliable, stay prepared, and keep thinking like an engineer.